Earlier on, we have already explained how to calculate the inverse of a function. Here, we are going to talk about the derivative of the inverse of an function. In order to understand the derivative of the inverse of the function, we have to recall the important properties of the function and its inverse. Say if you have a function y equals to f of x, the inverse of it is obtained by reflecting the function on the y equals to x, and this is what you will get as the inverse of the function. Here we are showing a general function that is 1 to 1, and for all the function that is 1 to 1, it has an inverse. When you want to compare the two functions, imagine you have a point on the original function at a, b. Here, a is the values of the x variable, b value of the variable y. If you were to construct the inverse of the function of fx, every single point on the function is reflected about the y-equals axis and map it onto the point on the inverse. So the point of a, b on the f function is mapped into another point which has the coordinate of b, a. The point of p and q is a pair of points that is obtained from each other by making a reflections about y equals to x. The reflections is represented by this point reflected into this point, and they make a 90-degree respect to this curve. Okay. So it's an so-called reflective operation. So when you want to compare the two curves, you have to consider these points on the two curves correspondingly. Now we want to ask questions, that is, given the derivative at the point x equals to a, what is the derivative on the inverse function at the point x equals to b? The derivative of the function at the point a has a correspondence to the derivative of the function f inverse at the point x equals to b. So you have to be careful when you compare the derivative of the function. So here you are comparing the derivative at the function at the point p to the derivative of the inverse of the function at the point q. In point p, the coordinate of x is a. In point q, the coordinate is b. There is an relationship between the derivative of the function f at a and the derivative of the function inverse at point b. The relationship is given by this. That is, the derivative of the inverse of the function at the point b is simply related to the derivative of the function at the point a by this inverse relationship. So here, b is the values of the function when you slot in a. This is one way of expressing the relationship between the function and its inverse. There are also other ways of saying the same thing. Here you can also say that the derivative at the point a is equals to 1 over the inverse derivative at the point b, and b and a are related. This is the graphical representation that represents what I mentioned just now. So this is a curve of f, and you are looking at the derivative of the function at point a. On the right hand side, you have the curve of the inverse of the function, and you are looking at the point BA. So this is the Q, this is the P that I mentioned earlier on. Then you will compare the derivative here and the derivative here, where this is the derivative given by the derivative of the inverse at the function B. So here I'm writing sometimes this as f inverse prime at B. It simply means you take the derivative of the inverse of the function, then you evaluate it at the point B. Here, sometimes I write it as f prime a, simply means you take the derivative of the function, which is f prime, then you evaluate the function of f prime at x equals to a, and they are simply given by this very simple relationship. So this relationship, that is f prime b, well here, f inverse prime b equals to 1 over f prime a, which is this statement, can also be written in this form. Now, how do you see that? Let me rewrite this statement again to make it clearer. What I'm saying here is that the inverse, the derivative of the inverse of the function at the point b is equal to 1 over derivative of the function at the point a. And then b and a are related. So here, if b is the values of the function at x equals to a, then equivalently, the statement can also be expressed in terms of the inverse. That is, a can also be expressed as f inverse acting on b, right? So these two statements are actually equivalent, right? B is obtained when you slot a into f. This statement says when you slot in to f inverse the values of b, then you get back a. So what am I going to write here is that I'm going to replace the expression of a by this. So the statements here that you have 1 over f inverse, this is expression of 1 over f prime a. So this is to say that you take the derivative of f, this is f prime, then f prime is a function of x, then you replace the expressions of the argument x by a. So this is just what this statement means. Okay, it's just expressed in a different notation. But here, a is known to be the values of the f inverse evaluated at b. So the values of a can also be expressed as this statement, df dx. The expression of df dx is calculated at the point where you replace x by the f inverse of b. Okay, where this statement is coming from the fact that a is equals to the inverse of b. So that is the statements that is given by the graph by this expression here. So it basically means this. It basically means the derivative of the functions, the derivative of the inverse of the function evaluated at the point of x equals to b is simply equals to this. It simply equals to 1 over the derivative of the function of f. This expression is an derivative of f. So this expression has a form of the function of x. Then what you do is that you replace the symbol of x in this expression by the inverse of the function evaluated at b. Okay, so if you look at this function, then left hand side is b, right hand side is also b. So in other words, this b is just a dummy. You can replace this b by anything, okay, because left hand side and right hand side are the same. So in general, the derivative of the inverse of the function at any values of b or any values of a, sometimes people write this as simply as x, is simply equals to 1 over the derivative of the function evaluated at x equals to the inverse of the function. Okay. So in other words, what you can derive from this very simple relationship is this. If you know what is the original function f, and you know what is the derivative of the function f, then you take the expressions of the x in the derivative of the function and replace it by the expression of f prime, then you'll be able to get the derivative of the inverse of the function. This is called the theorem 1, the derivative rule for the inverse. I'm going to apply theorem 1 in example 4. So here I have a function y equals to x squared, and it is limited to only x positive. So I'll call this y equals to fx equals to x squared. And my purpose is to find the x of the inverse. Okay, how do I proceed? I'll proceed this by using the formula that the derivative of the function at any point of x is simply given by 1 over the derivative of the function evaluated at x, where x is to be replaced by the expressions of the function. So people get confused because of these statements, which is the second step in the calculation. So I'm going to demonstrate how you do that. So first of all, let me do the step number 1. Step number 1 is to calculate, given the function of f, you calculate the df dx. So step 1 is to calculate what is df dx. So df dx is easily calculated to be 2x. Step 2 is to replace the expressions of x in df dx by the expression of f inverse. So in that step number 2, I have to first know what is the expressions of f inverse. So f inverse for the function fx equals to half has been explained earlier on in the previous calculation. The inverse of the square is square root of x. So this is expression of the inverse function. So the step 2, which is df dx, where I'm going to replace the expression of x by the inverse of x. This sometimes is written in this form, that is, you replace all the x by the expression of f inverse. So let me write down this step number 2 in more detail. df dx, according to my calculation from the first step, is 2x. Right? This is just the expressions of 2x. And the second step is to replace the expression of x by the inverse of f. The inverse of x is just square root of x. This statement means you replace all the x by the expression of square root of x. So that is this. So the square root of x here refers to the inverse function. So in other words, this is a mathematical operation that says whenever you see an x, you replace the x symbol by the expressions of the inverse, which is just the square root. So this is just equals to 2 times x replaced by the square root of x. That is what I have done for calculating the step number 2, but the calculations for the derivative is 1 over the result obtained from step. So you can check quite easily that indeed the derivative of the inverse of the function is 1 over 2 square root of x. The expression of the derivative of the inverse of the function is obtained by using this formula, which is just the theorem number 1. You can check that indeed this is equals to this by referring to the explicit expressions of the inverse function, which is x of a half. So here you also obtain half of x minus half, which is 1 over 2 of square root of x. So the derivative of the inverse of the function based on the expression of the function is this. This is expression obtained by performing the derivative on f inverse itself directly, whereas here the result is obtained by using the formula from theorem 1. So you can check that indeed the derivative for the inverse of the function is indeed correct. Okay, so you can arrive at this result by either taking the derivative directly on the inverse of the function, or obtain it by using the theorem 1. And you can represent the two functions, the original function and its derivative onto the curve. So this is a function x squared. This is the inverse function, which is square root of x. Then the derivative here and derivative here are comparable. So here you find that in this case, the derivative at this point here is just 1 over the derivative at this point. So here the derivative is 4, whereas at this point the derivative is 1 over 4. And you can see this quite easily from figure 7. So let us look at another example. You are given a function fx and you are asked to find the derivative of the inverse of the function without deriving the inverse. So here is a good example of x cubed minus 2. So you are asked to find the derivative of the inverse of the function. And you are asked to do so without knowing what is the inverse of the function. So in order to obtain the derivative, you don't have to calculate the inverse of the function. Remember, to calculate the inverse of the function, you have to go through a procedure where you make x as a title of the function, then you replace all the x by y, y by x, and then you express the right-hand side of your formula by f inverse. So to obtain the inverse of the function required some calculation, but here it is to be shown that you can calculate the inverse, the derivative of the inverse function without knowing the exact expression for the function. Okay. So you can calculate this by using the formula of f prime of x, where x is to be replaced by the inverse of the expression. So the questions actually give you some hint. It says you're asked to find the values of the derivative at the point 26, and then you are asked to find the values of the derivative of the inverse at x equals to 6 without a formula for inverse. So let me try to explain what this means. So here the question says you are asked to find the expression for this when x is equals to 6. Right. So this is the question. The question asks you to find what is the function at the inverse when x equals to 6. So imagine that you have a point of a function. Say this is a function y equals to fx, then the inverse of the function is f inverse. And the question says, you are asked to find the point of 2, 6, okay, and 6, 2. So here you're asked to find what is the values of the derivative at this point, x equals to 6. And then you can actually map this point to this point here by making a reflections about the y equals to x-axis. So this is a point that's mapped to here. So if here you have an x equals to 6, then at this point the coordinate of y would be then equals to 6. So here is a coordinate of 6. Then the value here is a number that you can calculate quite easily. Say here if it's 6, then the point here on the curve y equals to x would have n values of x equals to 6. So I think I have labeled this incorrectly. So let me drop this off. This point at the coordinate y equals to 6 on the inverse function corresponds to a coordinate of y at 6 on the y equals to f function. So here you are given the fact that the functions is x cubed minus 2. So this is x cubed minus 2. So if you know what is this value, which is 6, can you calculate this value? So this value can be easily calculated because you know what the function is. So let us try to calculate the coordinate of this point that sits on the function f of x. So you just set x cubed minus 2 equals to 6. So then x cubed is equals to 4. X cubed is equals to 8. Then x is equals to 2. So you know that here the values of the x coordinate is 2. So in other words, this point, when it's reflected onto this point, then these x and y will replace each other. Therefore, the coordinate here is just simply equals to 2. Okay, so the first step is you work out what is the coordinate on the inverse of the function when x is equals to 6. So you know that this is a point that sits on the curve of the inverse of the function, and its coordinate is 6. So now your job is to find out what is the derivative of the inverse of the function when x is equals to 6. Okay, so that means you need to know what is the derivative at this point. So if you know what is derivative at this point on the curve of y equals to fx, then the derivative at this point just simply equals to 1 over the derivative at this point. So now the question of finding the derivative on the inverse function at the coordinate x equals to 6 translate into finding the derivative of the original function at the point when x is equals to 2. Okay, so that is what I meant by translation. The questions of finding this quantity become the question of finding this quantity. Okay, then when you found this quantity, then you can calculate this quite easily. Okay, so you have df dx. So df dx is simply given by a very simple expression. From here, df dx is simply equals to 3x power 2. So here we have 1 over 3x squared, and then you are going to replace x equals to 2. Then you have 1 over 3 times 4, which is 1 over 12. So let me see, that is the correct answer. So the conclusions of this example is that you can obtain the derivative on the inverse of the function without knowing the explicit expression of the inverse function. You just simply need to know what is the original function and its derivative. The derivative at this point 6, 2 has to be calculated based on the corresponding point of 2, 6. You apply the theorem 1 correctly, then you'll be able to answer these questions. What is the derivative of the inverse function when x equals to 6 by calculating the derivative of the function at the point 2, 6. Okay, so that is example 5. That finished up the discussions on the second part of topic the inverse function and calculating the derivative of the inverse function based on the derivative of the original function.